So hello everyone, welcome to this new video. So in our previous videos I have told you that we have discussed with the structures of FIR structures and IIR structures. Okay, both are from different modules and both are having several set of forms. Okay, one is direct form, cascade form, and all those kind of problems we have already discussed. So those who have not watched those videos, please I suggest you all to please watch that videos and also come and watch this video and like this video before you proceed and support us guys. Okay, so next concept we are discussing it about design of linear phase FIR filters using windows. Okay, so we have several set of windows. Okay, those windows are, one is rectangular window, Bartlett window, which is not so important. I guess most of the problems related to Bartlett window are very less. Okay, so yeah, I've just written it for your information, that's it. Bartlett window, Hamming window, HAMM, Hamming window, Hanning window, HANNING, Hanning window, and Blackman windows. Okay, these are the 5 kinds of important windows. Okay, these are the 5 windows which is there in your syllabus right now. We have still more windows, but those windows are not there in your syllabus, so that's why whatever is there in your syllabus, that much I have written it here. So design of these filters, how to, again very easy kind of problems, nothing much to headache in this, but if you should be knowing what are these 5 windows, and we have one several set of formulas for those windows. Okay, so let us see that. So here I have listed it, all 5 windows here. Okay, and for that I have listed several set of formulas. The first window is of rectangular window. For rectangular window, the value of the frequency response omega n is equal to 1. For a rectangular window, it is constant 1 for all the values of n equal to 0 to n minus 1. Okay, so these formulas you won't be understanding now, but you should be remembering this because these formulas are required when you solve the problems related to this. Okay, when you solve the problems related to this, you would be getting a brief idea about how these formulas are getting interlinked. Okay, so this is for first rectangular window. The value of omega n is equal to 1 for all the values of n from 0 to 7, 0 to any number of values given in the question. It is 1. It is a constant 1 for all of them, and it is 0 elsewhere. Similarly, for Hamming window, the value of omega n is equal to, this is one term here, so that's why I've told you to remember, because you cannot understand this. So omega n is equal to 0.54 minus 0.46 cos 2 pi n small letter n divided by n minus 1 for all the values of n up to 0 to n minus 1, and it is 0 else. Okay, so this is the formula for Hamming window. This we should be putting in the calculator as a standard equation and substituting different values of n that varies from 0 to n minus 1. N minus 1 is the length of the filter that they would be giving you in the question. This equation put in the calci and get the values of the standard values of omega n. Okay, that I would be explaining when I solve the problem. Okay, so next is Hanning window. For Hanning window also we have one separate set of value, that is omega n is equal to 0.5 minus 0.5 cos 2 pi n divided by n minus 1 for all the values of n tending from 0 to n minus 1. And for Blackman window, again we have one huge formula, that is omega n is equal to 0.42 minus 0.5 cos 2 pi n by n minus 1 plus 0.8 cos 4 pi n by n minus 1 for all the values of 0 to n minus 1. Okay, and next one is Bartlett window. It is not required, I guess, because the problems related to Bartlett is not asked. Yeah, so yeah, I'm just going to skip it. No, Bartlett window is not required, guys. These 4 windows are very important. First 4 windows. Okay, the formulas are very important. So like this, we have a separate set of 4 formulas here. Again, note it down, very important ones. Okay, so now let us try to solve problems and understand these formulas in detail. Okay, the problems are very easy. Let us it purely consists of integration. Let us see how to solve it. So yeah, this is one problem here. Let us see this problem and try to understand these kind of problem in brief. Okay, design of FIR. FIR stands for finite impulse response. Again and again I'm telling you guys, linear phase filters using windows. So this is the problems here. This is the one problem. Let us see this problem in brief and try to understand it. The problem is design a symmetric FIR low pass filter. LPF stands for low pass filter. FIR low pass filter with the value of cutoff frequency omega c is equal to pi by 4 radian per second, and the length of the filter n is equal to 7 they have given here. Okay, and they have asked us to use the rectangular window. Okay, this complete problem would be coming for around 8 marks. Okay, we have one more these kind of problems which would be coming for 10 marks, that has one more additional step. In this problem only we have one more additional step. Okay, that we are going to discuss in our later sessions. Before that, let us see how to solve these kind of problems. Okay, very simple. First thing is, our goal is, for the given condition, we should be trying to write the value of HD of omega. Okay, HD of omega. So what is this HD of omega? Let us see. Before that, I forgot to tell you one simple logic. They have given low pass filter, right? So that how it is related, I am going to tell you. Okay, so what is generally a low pass filter? A low pass filter means it allows only the lower frequencies and blocks the higher frequencies. That is, all the higher frequencies values would be equal to 0, and all the lower frequency values it would be allowing it. Similarly, high pass filter, it blocks the lower frequencies and allows the higher frequencies. Okay, and here it blocks the higher frequencies and only allows the lower frequencies. This is the basic definitions of low pass and high pass filter, which you know. Okay, so for low pass filter we have only one single limit, one single integral. That is, from if we have the value of omega c as 1 radian per second, the interval is from -1 to 1. Similarly, if we have the value of omega c as pi by 2 radian per second or any values, the interval would be equal to -pi by 2 to pi by 2. Okay,